right. X-ray production and interactions, how radiographic images are captured. Now, first things first, we have the X-ray tube. So this is a picture of the X-ray tube. You have two sides. The cathode side, or the negative side, is on the right side there. And on the left side of the image there, we have the anode, or the positive end. Now, the cathode side of the tube is a location for something called thermionic emission. This emission occurs when the cathode is overloaded by the heat caused by the high amount of electrons that build up there. The electrons begin to boil off because of that heat. So those electrons now become free electrons, which is all happening very quickly inside of the X-ray tube. So accelerating those electrons. At kilovoltage, or kV, is applied within that tube, causes something called electrical potential difference between the anode and cathode. As you can see here, we have the cathode side and the anode side within the tube. And this car here in the middle is going to represent our electrons that are moving from the cathode to the anode. They move at a half the speed of light pace, which is incredibly fast. So on the anode side of the tube, which is where the electrons are moving toward, is a small disk. The disk is made up of tungsten or molybdenum. The electrons hit the disk and are abruptly stopped. This abrupt stop causes a release of energy in the form of an electromagnetic wave, and more specifically, it's X-rays. So you see here we have the car, the electrons, hitting the anode and producing X-rays. Those X-rays are a product of two different types of interactions. You have Bremsstrahlung interaction and characteristic interaction. Before we talk about these though, let's take a look at the anode itself. Now the anode, or that tungsten disk that we had talked about, just like everything else, is made up of atoms. So in this case, here is a tungsten atom. Now, when the accelerated electrons come into contact with the atoms in the disk, some of the electrons travel very close to the nucleus of this tungsten atom. The electron is slowed to almost a complete stop. Now, if you remember that the electrons are traveling at half the speed of light, it's going to be more like a crash than a slow stop when it finally comes to a stop. So it'll be more like a crash, and you have something called the law of conservation of energy, which means it doesn't just wipe out the energy still exists, and now it's moving forward in the form of X-rays as those electrons stop. So don't get too confused here. Seems confusing at first, but it's simple. Energy can never be destroyed or created. It always exists. It just changes forms over time. So in this case, the energy of the electron that is suddenly stops keeps moving forward. And like we said, it changes form to X-rays. So that was Bremsstrahlung. Now we have another result of the accelerated electrons. Basically what happens here is you have an electron that travels in towards the nucleus, misses all the electrons in the surrounding layers, and it collides with an inner shell or K-shell electron of that tungsten atom at the anode. So the original electron is deflected backward, while the collided electron, here shown in blue, is ejected from the tungsten atom in another direction. So the original one comes back, and the other one moves forward. Now, here's what's important about that. If you look at the green arrow here, that's where that electron that was collided with in the tungsten atom originally was. Now what happens is you have a void in the electron, in that atom's shell. So another electron needs to move down in order to take its place, or else the atom will be unstable. So when it moves down, it releases energy in the form of X-rays. So first one up here is the first part, where the electron comes into contact with the K-shell electron. moves it forward. And then the second part here moves on another electron moves down into the K shell to fill that void, and X-rays are released. So, just to recap real quick, two ways that radiation is created at the tungsten anode. So this is within the X-ray tube itself. You have Bremsstrahlung interaction and characteristic interaction. So in order to not get them mixed up, you can remember this little trick for characteristic, which is thinking about it as a TV show. So if a main character dies, another one has to take its place. So electron replacement, characteristic, and Bremsstrahlung is the other one. So let's talk about that beam itself, the X-ray beam that's created within the tube and shot out. So X-ray energy exists in the form of a wave, and like all waves on the energy spectrum, X-rays have a unique wavelength and frequency. So before it gets too mumbo-jumbo-y, we have to explain what wavelength and frequency are, because they're actually pretty simple. So all we have to do is look at a wave. When looking at a wave, we can easily recognize that it's just a pattern of up and down curvatures. So if we trace a piece of the wave before it repeats itself, that is one complete wave. This pattern repeats over and over again, and the length over which this single piece of wave occurs is known as the wavelength. Frequency, on the other hand, is a measure of just how frequent the wave repeats itself. A longer wavelength will take longer to repeat. Therefore, the frequency will be low. Repetition is low, frequency low. On the opposite end, short wavelength means they're closer together, and it means a wave can repeat many times in a short period. It has a high frequency, of course. So wavelength is length, whereas frequency is a rate of repetition or how frequent. The X-ray beam travels in a straight line and has the potential to ionize matter. So it's ionizing radiation, which simply means it has the potential to remove an electron from the orbit of an atom. Now, this is important because when an atom is ionized, it becomes charged. This can cause harmful effects within the patient's body. However, the risk is usually outweighed by the benefits of using radiation for medical purposes, such as X-rays. X-ray beam has a few characteristics that can be controlled by us, the technologists, which include quality and quantity of the beam. The quantity, in terms of X-ray beams, really just means the quantity of photons within that beam. So this can be controlled by the radiographer by selecting a setting on the console called MAS, which means milliamperage seconds. So you select a milliamperage, and then you select an amount of time. When you multiply those together, you get the milliamperage times that amount of time is the total mass that you're sending out. Now, quality is a little different. So when referring to X-rays, it refers to the average energy of each of those photons. So think of it this way. Let's use cars as an example again. We'll use a different one so it doesn't get confusing with the electrons as X-rays this time. Think of higher energy as a higher speed of a car, lower energy, lower speed. So imagine that the X-ray is going towards a patient as a crash test scenario involving a single car and many layers of drywall that it'll be crashing into. The higher the energy of the photons, the more penetrating the ability of those X-rays. So you have a car, it's going fast, it's going to go through more layers of drywall, clearly. You have a car that's going slow, it's going to only go through a few, and then it's going to get stuck. So that's basically the same thing that happens with the penetration energy of the X-rays. High energy, it'll go through more body tissue. Lower energy, it will not go through as much body tissue. So how does it interact with the actual patient? The primary beam leaves the X-ray tube and heads towards the patient. So when the beam comes into contact with the patient, some of the photons exit out the other side of the patient while others stay in the patient, depending on that energy that penetrating energy. So if it has a lot, it can go all the way through the patient. And if it has less, more of it will get stuck inside the patient, just like the car in the drywall. So the beam that leaves the patient is slowed by the patient, ultimately exits and hits the image receptor. This is what's known as remnant radiation, and it's ultimately responsible for actually creating the radiographic image. So let's apply what we know to practical use. When imaging patients, we can use something called the inverse square law. The inverse square law is used to calculate the relationship that exists between the distance of the beam, the originating point of the beam, and the patient. So this law basically states that when the distance between the source of radiation and the patient is halved, the intensity of the beam is quadrupled. So if the distance decreases, the intensity increases, and vice versa. So mathematically, it is intensity 1 over intensity 2 equals distance 2 squared over distance 1 squared. When applying the inverse square law, we can see just how effective distance is when it comes to protecting yourself and the patient. So remember to use distance to your advantage whenever possible. And that's it. And here are the sources that I used.